Hello, today we're going to be looking at Lab 5, the final lab of Physics 1, titled The Floating Slinky. Now the setup for this lab is we're going to be looking at a video in which a slinky is held from its top end and has been allowed to extend towards the ground into a static equilibrium state. The slinky is going to be let go, as you'll see, and the top end will immediately begin to drop towards the ground while the bottom end remains suspended in the air until the slinky completely collapses. And we're going to be modeling the motion of the top and the bottom ends of this slinky while they're still stretched out. Now the only physics principles we're going to be using for this lab are the momentum principle and the equations for gravity, drag, and spring force, because these three forces are the only ones that are acting within our system, and so they're the only components that we're going to be including in our model. Before we get into the model, let's ask the question, why does the bottom of the slinky float when the top is initially dropped? Now, in order to answer this question, we have to understand that although in our model, for simplicity's sake, we're going to be including just one spring force, there's in reality many spring forces that are happening within the slinky. And if we consider the fact that in order for there to be static equilibrium, there must be zero net force, everything starts to kind of fall in place. All the spring forces within the slinky are equal, but when the top of the slinky is released, it causes the first spring to relax, resulting in an imbalance that causes the second spring to relax. And this creates this chain reaction that follows down the length of the slinky. However, each individual spring force remains the same as if the slinky were never let go until that chain reaction reaches it, which means that this very bottom of the slinky will not change because this spring force is still equal to the force of gravity until the chain reaction reaches it, which means that only when the slinky completely collapses will the bottom finally begin to fall. Here's the video in Tracker where we plot the motion of the top and bottom of the slinky. We will use this data later in our analysis. Here is our computer model in which we set the bottom spring force equal to the force of gravity, allowing us to solve for the spring constant. And then we have a loop in which we iterate through and calculate the motion of the top and bottom of the spring. And these are our results. Here is a graphic visualization of all of our data. The red and blue lines represent the experimental data, and the yellow and green represent our model. As you can see, the model data pretty well predicts the kind of motion, yet it falls short in predicting how fast the top of the spring will reach the bottom of the spring, which will in turn will affect when the entire spring begins to fall as a whole. One reason for this is that we were not able to find the exact mass and relaxed length of the slinky. We had to make educated guesses on those, and so those could account for the discrepancy. But as you can see, many of our predictions did line up with the results that we obtained. That concludes Lab 5 of Physics 1. Thank you for checking in, and I hope you have a wonderful rest of your semester.